Hello, today's lecture is on the subject of tangent planes. We're going to continue exploring the use of partial derivatives, connecting them to geometric objects, in this case a plane that is tangent to a surface, typically at sort of one point, in the same way that tangent lines are tangent to a curve at one point. This was a task that we had to do every once in a while in Calculus 1 to construct a tangent line to the function y equals f of x. Here you've got your curve, y equals f of x, and here you have the tangent line to that curve at the point x naught. Now, this was, of course, these tangent lines have slope equal to the derivative of the function. And so we have the value of the tangent line at x naught equals the value of the function y naught. And then it also has the same slope as the function at that point. And so the way we construct these lines, if asked, is to use point slope form. We've got the point x naught y naught, and we've got the slope m equal to f prime of x at that point. And so we can set up this equation for the line. For what we're about to do in a moment, I just want to point out that if you had to create a vector that had the same direction as this line, you could say, well, if I go over 1, then I would go up an amount equal to the slope. That's the definition of the slope. And so the vector 1 comma slope, or 1 comma f prime of x, would give you a vector version of that tangent line. Which is what we'll need in the following example for 2 dimensions. All right, so just a bit of review. Now let's move on to multivariable functions, say functions of 2 variables, z equals f of x and y. And we imagine having some particular point x and y at which we are going to find tangent lines and construct a tangent plane. So if the goal is to find a plane whose value is equal to the value of the function, then the generalization of also having a slope equal to the slope of the function would be to have a normal that points in the same direction as the normal to the surface. So what would that entail? It would mean that the normal of the plane is perpendicular to both of the tangent lines. Okay, so this obviously makes us think that we're going to be using a cross product here. But first we need 2 vectors. And we can construct those vectors just like we did in 1 dimension in order to get a vector version, vector given the direction of the tangent line in the x direction. We take the slope in x, which is the x derivative of the function f, and then we have the vector going over 1 in x. We would go up by an amount equal to partial f partial x. And so this vector points in the direction of the tangent line. Similarly, if we want a vector version of the tangent line in the y direction, right here, then actually that would be over here, since y is increasing. Then we could go over 1 in y, and we would go up or down by an amount equal to the derivative with respect to y. So this right here is a way to construct vector versions of both of those tangent lines. And with those 2 vectors, we can now construct a normal that is perpendicular to both of them by taking the cross product v1 cross v2. So you guys are by now experts at taking the cross product. You can do it in your sleep. And so if you like, you can set up this sort of pseudo matrix, ijk, 1, 0, mx, 0, 1, my, and we take the cross product, and we get this vector right here, negative mx, negative my, comma, 1. So this is the direction of the normal vector that is normal to both the tangent lines, normal to the surface, and therefore normal to the tangent plane. So we now have a point. We have the point x naught, y naught, z naught, and we have the normal, which means we can use point normal form of a plane to construct the tangent plane. So we have our point normal form. Always remember this before you remember anything else, and what we're doing is just plugging in. This is x naught, y naught, z naught, this r naught, and this n right here is the minus mx minus my 1. So we plug that in. minus mx, x minus x naught, minus my, y minus y naught, plus 1, z minus z naught equals 0, point normal form. We do a little bit of rearranging. And what I've actually done here is, instead of putting it in standard planar form, I have put it into the form of a function z depending on x and y. And I've left these things here, the x minus x naught and the y minus y naught, multiplied each by the slope. This looks a lot like point slope form of a line in Calculus 1. Up here, we would have written y equals y naught plus m x minus x naught. And so I've preserved that form down here when I do the same thing in 2 dimensions with a tangent plane. Of course, if the tangent plane happens to be vertical, you would not be able to write it in this form. However, we are dealing with functions z equals f of x and y already. And so what would a vertical tangent plane would mean would be an infinitely steep surface, which would be a point of discontinuity in such an equation. So if we're starting from the form of a function z equals f of x and y, then we're never probably going to get a vertical plane, and we can usually always put the tangent plane in this form. Okay, so that's the basics of tangent planes, how to construct them. You can construct them with this RU cross, with the cross product of the 2 tangent vectors. And here's an example. So we're given a surface, z equals 4 minus x squared minus y squared, and we're given a point on that surface, 1, 1, root 2. You can plug in 1 and 1 and verify that that is indeed on the surface. And you might recognize this as the top half of a sphere. If we were to square both sides, we'd have z squared equals 4 minus x squared minus y squared, which means you could put these on the other side and get the equation for a sphere of radius 2 centered at the origin. So it's the top half of a sphere, and we're given some point a little bit of the way down the sphere, and we're asked to construct a tangent plane at that point. So we follow the instructions given in the previous example. We calculate mx, the slope in the x direction, which is partial f partial x. We get a general representation of that slope for any point xy, but then we plug in 1, 1, and so we get negative 1 over root 2 for that derivative. The slope in the y direction is partial f partial y. We plug that in. We evaluate at 1, 1. We get, again, minus 1 over root 2. I always say that drawing pictures is helpful if you can, and if you can draw this picture, you can check those numbers, at least the sign of those numbers, with your drawing. So here's the y-axis. If we move in the y-axis, we are indeed going down. Here's the x-axis, and if we move in the positive x direction, we are indeed going down. So these signs at least look correct. So I very rarely encourage formula use, but this one is quite common for reasons that will be seen below. And so I take these two numbers, minus 1 over root 2, minus 1 over root 2. You'll notice that here I've already, I use cross products to get a formula for the tangent plane, and I'm not going to take cross products here. I'm really just plugging these numbers into the formula. Here's my z naught, here's my slope in the x direction, here's my slope in the y direction, and here are my x naught and y naught values. So this is the form of the tangent plane in the z equals a function of x and y form. Now the reason I like this form and have just used it rather than constructing cross products, making you go through construction of cross products, is that this form is very closely related to an even more important concept than cross products. All right, and that is Taylor series. So if we think back to Taylor series in one dimension, hopefully the person you had that taught you about Taylor series taught you that they are used to approximate functions. So if we have a function y equals f of x, and we want to think about approximating that function, the tangent line is a reasonable approximation in the vicinity of the point in question. And so you can get the formula for the tangent line, which we just obtained earlier in the lecture, point slope form of a line. And then you can move this y naught over as I did earlier, and you have this form, y equals y naught plus slope times x minus x naught. It's just a variation on point slope form. However, what is y naught? Y naught is the value of the function f at the point x naught. And what is m? M is the value of the slope, which is the value of the derivative of the function f at the point x naught. And so this point slope form of a line could be rewritten y equals f of x naught plus f prime of x naught times x minus x naught. And these you should recognize as the first two terms, or the zeroth and first term, of a Taylor series. And if you wanted to keep going, you would get plus f prime prime of x naught over 2 factorial x minus x naught squared, and so on, right? So really the tangent line is a truncated Taylor series, keeping the constant term and the linear term. The line, the linear term. So the vocabulary kind of lines up. This is a very powerful idea that Taylor series give you approximations to functions. It's outside the scope of this lecture, but if we had, this gives you a linear approximation of the function in the vicinity of x equals x naught. If we kept the next term in the series, it would give us a quadratic approximation of the function, which would be accurate over a wider range of x's. And we'll talk about this a little bit more in the supplemental lecture that accompanies this one. So anyway, very, very important concept that tangent lines are related to Taylor series in 1D. So too, now moving back to our topic, so too, with two independent variables, the tangent plane is equivalent to what we call a 2D Taylor series. So here was our form of the Taylor series. We had our z equals z naught plus mx, x minus x naught plus my, y minus y naught. Okay, those were the value and the x slope and the y slope terms in the tangent plane. But again, what is z naught? Z naught is the value of the function f at x naught, y naught. What is mx? It's the partial derivative of f with respect to x at the point x naught, y naught. And similarly, my is the partial derivative of f with respect to y at x naught, y naught. So we can replace this sort of shorter notation with this longer notation, and we see that it looks very, very similar to the Taylor series notation in one dimension. Indeed, this is what we would call the zeroth or constant terms and the first order or linear terms in a 2D Taylor expansion, right? So this idea is very, very similar. It's identical to what you see in 1D. This is just what a Taylor series looks like in 2 dimensions. And so the tangent plane is a truncated Taylor series in 2 dimensions. This is incredibly important, which is why I am emphasizing this representation of a tangent plane over the one obtained using the cross products. All right, so I'm not sure how much of that was in the book. The book does briefly talk about the use of tangent planes, or as I will call them from here on out, linearizations or Taylor series, in approximating functions. All right, so we've got our function z depends on f x y. I don't know why that's there. And we say, okay, I'm going to construct the tangent plane or the linearization of that function, keeping only the constant terms and the linear terms, and I'm going to call that an approximation of the function. And so if the point in question is near x naught, y naught, then the linearization is going to be near the value of the actual function. So here's an example. It says here's some function, some made-up function that is got x cubed y and 3xy. Find the linearization, that is the equation for the tangent plane, and use the linearization to approximate f at the nearby point 1.1, 0.9. So I go through my work. I calculate the derivative in x. I calculate the derivative in y. I evaluate those derivatives at the point 1, 1. I get 6 and 4. I plug into my formula. Again, I rarely like to use formulas, but this is just so powerful. Formula for the Taylor series in 2D. I've got my 4, the value of my function at 1, 1, my slope. I get my expression for the linearization here. Now, the idea is that the linearization has a value nearly equal to the value of the function at nearby points. So let's go to a nearby point, 0.1, 0.9. All right, so I have 4 plus 6 times x minus 1. Well, x here is 1.1. 1.1 minus 1 is 0.1. Plus 4 times y minus 1, that gives me negative 0.1. And I plug all that in and add it up, and I get 4.2. If I plug in the values 1.1, 0.9 into the original function with a calculator, I get 4.17. So it's a reasonable approximation. It's not a perfect approximation. It's not perfectly precise, but it's reasonable. And the equation for the Taylor series is much simpler than the original equation. And this is why Taylor series get used all the time. Here we have something that is what we would call nonlinear in the variables x and y. We have x to the third power. We have x cubed times y. We have x times y. And if you're trying to deal with nonlinear equations in general, they're pretty nasty, and there's not like a general method of solving nonlinear equations. Linear equations, there are all kinds of methods. There are all kinds of wonderful things we can do to solve linear equations, and so it is very often useful to approximate a nonlinear equation with a linear equation. And that is exactly what a Taylor series does, what the linearization or tangent plane approximation do. Final note, no example to follow, but we should point out that this kind of procedure can also be done in more than 2 dimensions. Okay, you just have, say you have 3 variables, then instead of 2 linear terms, 1 for each of the x and y directions, you now have 3 linear terms, 1 for each of the x, y, and z directions. So if we had some point, x naught, y naught, z naught, at which we wanted to approximate the value of some 3 variable function like t, say the temperature in a room with 3 dimensions, then the Taylor series representation or linearization of that function would be the constant term, t of x naught, y naught, z naught, and then 1 derivative term for each of the 3 variable directions, which together constitute the linear terms. The derivative with respect to x times x minus x naught, plus the derivative with respect to y times y minus y naught, plus the derivative with respect to z of z minus z naught. And so on. You could do this with 4 variables. You'd have 4 terms, and so on. Now, if you think this stuff is interesting, that this Taylor series idea is pretty interesting, and perhaps you wonder what becomes of, say, the quadratic terms in the Taylor series, right? The constant, the linear, the quadratic terms, what do they look like? How many are there? How does this stuff work in general? Then there is a supplemental lecture that I will provide, sort of some honors or bonus content material that you may find interesting. But otherwise, that's all, and we'll see you in class.